I think I got in everything you said, so. Okay. I hope so. The question is, can he stick the landing? Can he do it in 25 minutes? And I don't know the answer to that. Yeah, well, actually that's good.
Okay, I'd like to have everybody reconvene. Hopefully you're all enjoying the workshop as much as I am. Thanks to the organizers, I've played only a very small role. So we're going to kick off the session this afternoon with Jason Tumlinson. He's going to tell us about the Habitable Worlds Observatory, a new age of cosmic exploration.
Okay, can everybody hear me in the audience, coast to coast and all the ships at sea? All right. I'm really glad to be able to come to you today and talk about what we're planning for the future after Webb, after Roman, the so-called Habitable Worlds Observatory. So you're probably wondering already, what is HabWorlds? Well, the easiest way to think of it is to imagine Hubble, but a lot more sensitive because it's a lot bigger. And its twofold science goals are to perform a search for life around nearby stars on Earth-like planets, and to perform a program of transformative astrophysics. So after this, you could go to sleep if you needed to. The one thing I need to make you understand, the one message I want you to leave this talk with today, is that this observatory is for everybody, all astronomers, all areas of science, and not just the things that are mentioned in the name. Everybody got that? Okay. Somebody back there didn't raise their hand. How did we get here? Well, you probably already know that astronomers gather every 10 years to do a decadal survey, and the largest flagship that is recommended by the decadal tends to fly. Hubble, Chandra, Spitzer were the first generation of great observatories, then Webb. We're looking forward to Roman in a few years. But it's really important that there's about 15 to 20 years between recommendation and launch. And that means that there's actually a really long process of development in between conception, which for Webb occurred, you might say, at a meeting in this room in 1989. And I'll remind you, that was before Hubble launched. So it was quite bold to be envisioning the next big thing before Hubble was even in flight. But, you know, here we are a few decades later with the beautiful results coming out of Webb, which you've heard so much about this week. It's basically the same situation with Roman. Roman's a little simpler. Roman is using a pre-existing telescope. So the time frame isn't quite as long, but it's the same story. For Habitable Worlds, I think I may have to stay on this side. That story starts back as early as the late 90s, but the part here I'm showing you goes back to the middle of the last decade when our parent company, Aura, put out a report called From Cosmic Birth to Living Earths. That went through the decadal survey. The decadal survey made a very strong recommendation for what is now called Habitable Worlds because Bill Nelson, NASA administrator at the end of 2022, said so. That's where the name comes from. So in between the conception and this beautiful science observation, this happens to be my favorite Webb image, is a tremendous amount of work. And I would say that following some of our forebears here who built Hubble, the four virtues we need to have are vision, teamwork, optimism, and patience. So I'm going to strike a few of those notes as we go along. And here's the path Webb followed from that initial conference through very early yardsticks. This is a hand-drawn diagram by Pierre Billet, who was an engineer here. And it kind of looks like the real thing, and this is from the early 90s. Then the decadal recommendation, the science working group started up in the early part of the 2000s. There was what we call a near-death experience in 2011. and a significant replan leading to lots of hard work on here and on part of many, many other people up until a very successful launch. So flagships are hard, but they allow us to see ourselves in a new cosmic perspective, right? This is a beautiful image from Janice Lee and the FANGS project showing the contrast between Hubble's view of this galaxy and Webb's view of this galaxy. I think this is a profound statement about what is possible. So it really lets us appreciate, where we stand in this cosmic context. So another way to think about what is HWO, as I said, it's a super Hubble to search for life in the universe and perform transformative astrophysics, is the hardware way. This, it's a device, right? It's going to be an ultra-stable telescope so that it can do the high-performance coronagraphy. It's going to try to find Earth-like planets that are 10 to the 10 times fainter than their parent stars, but only about a tenth of an arcsecond away on the sky. That's what the coronagraph is for. We'll have a high-resolution imager, which is diffraction-limited imaging down into the optical. So that's where you're going to get your prettiest pictures from. And then all the useful science will come out of the multi-object spectrograph observing in the UV, which is my favorite instrument. And we're definitely going to talk about all the aspects of these instruments as we go along. This thing is going to be more sensitive than anything you've ever tried to use before. Unprecedented depth. In comparison to other observatories here, we have worlds at a 6-meter scale and an 8-meter scale between 3 and 10 hours. And you can see that this puts 1 nanojansky or 32nd magnitude into the conversation, right? So imagine, now your brain should start racing and thinking, what am I going to do with this thing, right? It's amazing. Similar comparison with even the largest telescopes on the ground because of backgrounds and sky noise and the atmosphere will struggle to reach those limits of magnitude. So, if you're willing to invest a lot of time, going even below 32nd is possible. The imaging resolution, of course, being diffraction limited at optical wavelengths, puts you down well below 10 milliarcseconds, and that's going to deliver sharper images of anything you can think of on the sky. And because of the way cosmology works, there's sort of a maximum angular size of objects at any physical size. And so worlds will be able to resolve any object anywhere at any redshift to about 200 parsecs. If you would like to do calculations like this for yourself and say, what does this do for me? And answer that question. If you'd like to get involved in the committee work that NASA is doing right now, these are your resources to do that. So these are open source online community tools, exposure time calculators for the coronagraph, the UV spectrograph, and the imaging camera. So what can we do with this unlimited power? We're the good guys, don't worry. The answer is an amazing amount of transformative astrophysics. This is just one selection of slogans that capture the many possibilities. And I'm going to go through a few of these in a little bit of detail. But this is only, of course, then the very tip of what's possible once this thing is put in the hands of smart community astronomers like yourselves. So let's do a couple of examples. This is the beautiful fat image from Hubble's lovely survey of the Andromeda disk. This is 138 million stars and dust and gas. Beautiful image, especially when you see it full size out in the hallway when it's out. This is 818 orbits of Hubble imaging. But with a larger camera, a larger field of view, and more sensitivity, habitable worlds, this is one footprint of that imaging camera. You're going to go deeper, 4 magnitudes fainter in the same observing time, or just cover the area faster, right? What can you do when you have that imaging capability? You're turning images that used to look like this into things that look a bit more like that. You're resolving dense fields much better, up to 50 times denser in the same time. And if you look at one of the most interesting outputs of FAT was a pixel by pixel or bin by bin or region by region star formation history for the whole disk. So you're talking about being able to do that with much greater efficiency, drilling down much further down the color magnitude diagram and into denser fields, pushing this into the bulge, pushing this into dense star-forming regions that otherwise were not possible. But we can do a lot more than that because every region on the disk of this galaxy has some kind of gas flow, whether that flows out from feedback from supernovae or in through accretion from the circumgalactic medium. We know how to observe those things if we put spectroscopic slits down on them, right? But so far, we've been limited, very limited, by what Hubble can do in the ultraviolet. The COS aperture, isn't even this big, and you can only do it one at a time, right? Same thing with STIS, even though it's an imaging spectrograph, it doesn't do multi-objects so well. So with habitable worlds, what we're looking for is a multi-object spectrograph capability in the ultraviolet. This is a tiling of the FAT image with each one of these is like the FAT tiles, and there's 414 footprints of the multi-object spectrograph in this diagram. And in each one of those little green squares, the 414 of them, you can imagine observing 10, 20, 50 objects all at once. So now we're doing samples of tens of thousands of objects, watching the down-the-barrel outflows, watching the inflow into the disk, characterizing the dust, all this stuff at small scales that we couldn't do before. That's a rendering of what the microshutter, it's like the NIRSPEC device, the NIRSPEC microshutter array, but operating in the ultraviolet. Okay, so how many habitable worlds, how many Hubbles is habitable worlds when you do that imaging and spectroscopy comparison? In terms of imaging efficiency, it's about a factor of 8 from sensitivity, field of view, and overall system efficiency. But it's crazy when you get to the ultraviolet, because the ability to do multi-object spectroscopy in the same sense that we're already doing it with Webb really makes the multiplexing factor is the huge gain. So this is totally transformative in terms of our ability to watch the way galaxies acquire, process, recycle, and deal with their gas. This is why we call it a super Hubble or a Hubble for the next generation. If you like to take pictures of faint galaxies, you might have seen a few of these over your career. This is a rendering of what a faint galaxy, a redshift 2 galaxy at 10 to the 6 solar masses, so a pretty faint thing, at 30th magnitude. If we translate that to Hab worlds, you'll see that it goes quite a bit deeper, and you're able to see detail that you wouldn't see otherwise. Remember, I said you can resolve things at 200 parsecs or larger at any redshift. So now you're starting to see the internals of galaxy disks at high redshift. You're starting to see the way those things interact with each other. You're able to see instabilities in disks or look at the rotation or mergers of faint galaxies. It's all laid out there before you. That means we can actually start to think about seeing the bottom end of galaxy formation. In other words, there is a scale at which dark matter halos are no longer forming things we would call galaxies. They're starless. And that scale in dark matter is somewhere around 10 to the 7 to 10 to the 8 solar masses, inferred from local dwarfs or dwarfs in the Milky Way halo. But when those things were forming stars at high redshift, we can ask, would we be able to see those with a given telescope? And the answer is pretty much yes. We can see almost to the bottom of the Milky Way's merger tree at all redshifts because we have such revolutionary sensitivity. So seeing to the bottom of the galaxy formation process is another advantage. Galaxies also transform, massive ones do at least, and this is a beautiful disk galaxy. A lot of these turn into these. They go quiescent, they merge, they stop forming stars, and it's not really clear why. The quenching process is, to me, one of the most motivating factors in science. That's one of the reasons I do the research program that I do, is to figure out how this happens. And it may not surprise you to find that I think the circumgalactic medium is involved in that, or at least responds to it in the sense that studying the CGM of those transforming galaxies will tell us something about the process. Of course, it could be mergers, of course, it could be AGN, but I want to know how the gas supply responds, right? So this is a bit of a complexogram, but it shows that with Hubble, when we look out using quasar absorption lines to try to examine the CGM of galaxies in transformation, first of all, galaxies undergoing the active phase of transformation, of quenching, they're not in that phase for very long. And there just aren't that many of them out in space. So having a sight line to a distant quasar that runs past one is pretty rare, right? And that's especially hard if you're limited to quasars, at around redshift 0.5, and your UV coverage cuts off so that you can't see some of these important diagnostic lines at low redshift. So with Hubble, we're limited by two things: the brightness of the quasar we can observe and the wavelengths we can see. And that's just the coatings on the mirrors. So with Hubble, we've done hundreds of normal galaxies, and there's people in the room who've published papers on this, including me. And there are really only a very small handful that you could say might be galaxies that are actively transforming. They're just not that common. But with habitable worlds, we can go another few magnitudes deeper down the quasar luminosity function, and we can go to the very shortest wavelengths, which means we can do this stuff in the rest frame. We're close to the rest frame. And that actually changes our possible sample by a factor of about 30. So now we're doing thousands of normal galaxies and almost as many galaxies in active transformation as we have normal in our current samples. That's going to be pretty revolutionary. And maybe you don't care as much as I do, but I've just given you the contents of my cycle 1 proposal. So I hope you will have forgotten it by that point. He won't. There is a bit of a technical question, which is how far into the UV do we need to go? And this is a topic of active debate, because the coating on the mirror is the thing that determines how far into the UV you can go. There's been a lot of technology development on novel coatings, much better than the one Hubble has, which was deposited in the 1980s. The coating, I'm sure, is older than a number of people here in the room. We can do a lot better now, but there's doubt about, what's the largest optic you can put these coatings on? Are they going to disturb the coronagraph in some way so that we'll have to make a choice between the shortest wavelengths in the UV and the coronography? And this link is to the science working groups underneath NASA's current START committee that I'll describe in a moment, who are concerned with making this science trade now. So if you care about the shortest wavelengths accessible to this amazing UV spectrograph, this is your opportunity to stand up for science, raise your hand, and say, I need to get to 1,000 angstroms, and believe me, I'll be standing there with you. So let's move on a little bit. Astrometry. It always amazes me how precisely we can measure the motions of stars with Hubble and now with Webb. And we can actually measure the velocities of things that are moving quite slowly. So with habitable worlds, we're not only able to exceed the 50th of a pixel systematic floor, because the pixels are smaller, the telescope's bigger, the diffraction limit is better, and the imaging quality is overall better. But it's possible that with special calibrations or even a special astrometric device, you'll be able to get below the microarcsecond level, maybe well below the microarcsecond level. And at that level, essentially everything on the sky moves, right, in a detectable way. So it might take a couple of decades of data, like it has for Hubble, to catch something moving, but basically anything, anywhere. At 10 parsecs, if you have an astrometric sensitivity that corresponds to 10 centimeters per second, I've tried to draw real-world examples of things moving at that speed, right? So imagine actually measuring the motion of something that's moving about the rate of a giant tortoise, which is sort of like this, right? All the way up to jet airplanes and galaxy clusters. So if your science involves probing the relationship between baryons and dark matter, or the dynamics of stellar populations, or the internal kinematics of galaxies, this is the device for you. And you also need to stand up and say, I'm interested, I want to kick in my science. So that's a whirlwind tour of this slide, which tries to capture everything in all of astrophysics into one bento box. And I'm very serious here. You need to kick in and contribute, because what you are doing and interested in and need this for the most may not already be in here. Okay? So I hope I've convinced you that this is not just for the exoplanet people, but here we go. This, as I said, puts us in this cosmic context. Astronomy in general allows us to see how we fit into this grand scheme of dark matter, of the cosmic web, of baryons forming galaxies, and ultimately into disks. But let's remember our cosmic origins, right? Let's remember that it's literally true where we came from and where we are. So we're not only part of that Milky Way galaxy, but we're here on this little blue planet, and the other people who want to build this thing, this is what they're after, right? The pale blue dots. Why are they so seemingly obsessed with this? Well, we know that the Earth teems with life. We know it's a very complicated ecosystem. We know the traffic in Baltimore is pretty bad. But as biologists, and I mean literal biologists, evolutionary biologists, microbiologists, have worked out the exquisitely structured tree of life for our planet, all the way from the formation to that what they call the last common universal ancestor, which was a microbe or bacterium 4 billion years ago. And as you go around this tree of life from what we would consider to be simpler to more complex organisms, all that's been worked out. And this is the real tree of life based on DNA and other kinds of studies. And of course, you are here. But there's one thing the biologists can never do. This is something that is left definitely to the astronomers, and that's to answer whether nature has repeated this experiment anywhere else. Is this contingent? Did this only happen because this planet got lucky in its orbit, in its climate, in its composition? We really have no idea, right? Of course, people have discovered thousands of exoplanets, and a couple of hundred of them are known to be Earth size. This is a pretty big number, thousands. But you're used to seeing these pictures, but it's important to remember these are all artists' conceptions. We don't have a picture of an Earth-like planet. We have direct evidence that they're there. We have transit curves and we have radial velocity measurements, but we don't have a picture of a planet. So what might that look like? This is a simulation using the habitable world system, photon by photon, trying to estimate what it would look like to put our solar system at 10 parsecs or 30 light years and evolve it forward. So this includes the coronagraph. The occulting disk has already been added in there. The star would be there. And our solar system is evolving, and we're labeling the planets. There's Venus, there's Earth, and it'll evolve for a bit. Remember, this star is 10 billion times brighter than Earth, right? So this is already a tall technology challenge, but we believe it can be met with some more work in the lab. That's the image we're after. We want to see direct evidence of an Earth-like planet in a direct image. That's the goal for habitable worlds. And specifically, the goal of the decadal set was to search 100 nearby systems looking for up to 25 or approximately 25 Earth-like planets. But if I take the labels off and show you Venus and Earth, you wouldn't be able to tell them apart. Which one of those is nice and comfortable and which one of them is an uninhabitable hellscape? Right? They're both little bluish dots. So of course, in order to really, as I was alluding to before, in order to really do the hardcore physics, we have to have a spectrum. Oops. And what we'll be doing, sorry, slide snafu. What we'll be doing is taking a spectrum that has oxygen and methane and carbon dioxide and ozone. And in certain combinations, those things are unique. Let me see if I can show that to you. Rather unique signatures of life. There are combinations of those that the astrobiologists tell us wouldn't occur if you didn't have metabolism sucking in one molecule and spitting out another. On Earth, trees, plants take in the carbon dioxide, generate the oxygen, and we do the opposite. So spectra like these, maybe 25 of them, will tell us if any of those planets are inhabitable or inhabited and how many that might be. So it's pretty amazing to think that I might be able to take my own kids or my grandkids out and point up to a bright star in the sky and say, it's that one. We know that it's that one. It'll have a name. I'll be able to go out and see it. That's a really profound change to our thinking as humans on a pretty otherwise boring world. But so there must be something that ties all this together, right? So that's what I'm going to try to do in the next 2 minutes and 52 seconds. We all know the cosmic history going from the large-scale structure through galaxies to stars forming in galaxies to stars blowing up, producing heavy elements and stirring galaxies and then back around the cycle. This may have happened many times prior to the formation of the sun and the Earth here in the protostellar disk. And then we're asking the question, how often did those conditions get repeated to the point where life emerges on other planets? But what this means is literally the tree of life that the biologists have derived is rooted in the stars. Everything that led up to the formation of the Earth, its composition, its orbit, its history, comes from astrophysics. And we can tell that story with this observatory. Why? Because stars create the heavy elements. Now, we all know this, but we all take it for granted in a sense where we kind of forget that that's true. But when you go out and try to explain that to a normal person, it blows their minds a little bit, right? To think that ordinary matter was on the inside of a massive star, right? This means that we can actually tell this complete story in the sense that, you were here in the guts of an exploding star, right? You were here in the star-forming region that formed the sun and the planets. One of the things I'm most proud of having done scientifically is to show that a lot of heavy elements leave the galaxies before they come back, which means you were here too, probably outside the galaxy before the recycling under gravity brought you back in. So if we can find Earth-like planets and find signs of life in their air, then we can say, we have this history in common with any life we find on another Earth-like world. That's really profound. So to me, that's what ties all of this together, the astrophysics, the habitable worlds part of the observatory, into this great comprehensive picture, right? So now we've got the exoplanets living along with the astrophysics. And this is really the ultimate epic handshake, right, between both sides of a very strong case coming together. So let's very quickly, in the last minute, look at our history again. Here's where we are, right? We're back in the very beginning of this process. We don't know what happens here, although we hope to do all of this a little bit faster. We don't want to do that part. But this has to be a community effort, right? So there's many ways to get involved. You're probably not going to have a chance to do this right now, but if you check our website, you can volunteer for the working groups that NASA's running. You can join the community Slack space. We definitely need your ideas because the science cases are coming together this year. There's at least 2 relevant sets of working groups led by Janice, who's sitting right there, on the evolution of the elements. So that's like chemical evolution, stellar populations, star formation. There's another group, which Swara, I think, is here. Swara, raise your hand. And Mark is right there. And they're taking inputs on IgM and CGM, the dark sector, ionizing photons, and so forth. So there are plenty of opportunities to join and to provide input. We're looking for science cases. We're looking for science ideas that are novel. We're looking for an aggregation of science programs that provides us an idea of what the whole program of the observatory looks like. And most important of all, remember, this isn't just for finding Earth, it's for everything. So at that point, I will stop and take your questions.
Okay, we have time for a few questions. Well, I'll ask you a question then.
Okay.
So every great observatory has had a near-death experience. And so empirically, it's likely that this is going to happen.
It's true.
And if I'm being paranoid, I would fear that a descope of HWO jettisons the RUV. So
Yes.
Do you agree with that assessment, and what could the community do to kind of fight back?
Well, we're not there yet, but you're right. Near-death experience is a common thing, and like with Webb, where you were surely going to fly NIRCam and MIRI because they were the critical things. Here, the coronagraph is the thing that goes. So 2 thoughts. One is that the stronger the science, the better the case when you really need it. It may seem now like, well, someone else is going to cover that for me, because there are people here doing this and I don't need to get involved. But you actually do, because the weight of community support when the crises occur is critical. Second thing is there will be servicing built into this concept. So even though we won't replace the mirror, we will be able to replace the instruments and make those more sensitive or better in certain wavelengths or other capacities as time goes on.
All right. So get motivated. Yeah.
You mentioned the possibility of servicing mission to change or updating. Can you expand a bit how this will be planned to be done?
Yeah. So the power of servicing is really obvious when you compare Hubble with all the great observatories that weren't serviceable, and everybody has their private theories for why only Hubble got that and the others didn't. But the fact is, it made Hubble productive and grew its capability over decades in a way that we definitely want to be able to do again. Now, Webb, we knew it had to go to L2. We didn't have any servicing capacity at L2, and we still don't. So it was sort of in a historical dead end. With this, we want to go back to that because servicing is so powerful. The only catch is that infrastructure has to exist, and it has to be developed from outside of astrophysics, because we can't have NASA's Astrophysics Division pay for this observatory and others like it and all of the servicing capacity. But there's quite a bit of private industry, there's quite a bit of NASA interest in servicing spacecraft, certainly in low Earth orbit, also at L2. It probably would be robotic, and there are already engineering efforts underway to make that feasible. So it's not terribly far-fetched, and we certainly want to do it scientifically.
Okay, Sanch?
Yeah, you mentioned these instruments. How flexible are we in the design? Like, do we, for the first generation at least?
Yeah, so all those numbers that flash by on the instrument slide are all nominal. They happen to be parameters closely related to those instruments that were developed under the preceding LUVOIR and HABEX studies. But nothing is written in stone, nothing is even written in Jello yet. I mean, it's just, you know, it's fluid. They're studying, the TAG team, the technology team under NASA's group effort, is studying particular concepts. But right now is the time to ask for instrument modes to do your science that aren't on there. So if a UV IFU would be an obvious case. An optical band multi-object spectrograph would be another thing that isn't up there. So the door's open to things that aren't already specified. That door will close sometime in the next 3 to 4 years, so now's the time to get in.
Okay, we have time for one more question.
This is more like a general question for these sort of flagship missions, because I want to know how it works. So given that you're saying that the door is open for more instruments of, you know, all of our sciences, so when this entire proposal will go up, and if there is sort of like I guess some limitations for budget or technology or whatever, and if then some of those have to be cut out, will there be a ranked list when it's going to the next level for approval? Like, okay, if this is something that we definitely need,
Yes.
it would be good to have the rest or something.
Yes, so it is the science community's job to make sure that whatever flies does what the science community needs it to do. There are times when contractors, let's say, would fly a brick if that's what got them off the launch pad, right? So we have to be there. We collectively have to be there when those decisions are made. Now, it's not purely a scientific decision, because you might have something that's scientifically very compelling, but technologically almost impossible, or they've tried to build it and failed. So that tension, as you say, will happen, but all the more important for the scientists to be there to guide those decisions. And to be even more specific about it, that's one of the reasons this place exists, is to represent the science community at those stages of the process.
All right, great, thank you. Let's thank Jason
Thank you.
again.
Next victim. Oh, I can give you this back.
This is the wrong one.
Should take any actually.
Okay.
Both of them.
Is this on?
Yeah, so you just have to press this when you're ready to speak. Is that yours? Yeah.
Yes.
Okay, speak. All right, we all set?
Can you hear me? Yes.
Okay, great. So the
Thanks.
next talk is by Giovanni Cresci, role of AGN feedback in regulating star formation.
Thanks a lot. So first of all, let me thank the organizers to putting together this very interesting conference. So let's try to be at the level of all the rest. So the idea here is to discuss why most of the baryons are not condensed into stars. We know that at the low mass end, you can probably do it with the star formation feedback. For high mass galaxies, you probably need something more. And the idea is that the AGN make an important role in this. This is probably done through outflows. This is just two examples, one from the local universe with MUSE data, and one with NISPEC data and ALMA data at a higher redshift. The one thing we know is that these outflows are almost ubiquitous in AGNs. So this is a plot showing as a function of the distance from the main sequence and as a function of mass, the fraction of AGN outflows in the general galaxy population. And you see, if you go to high mass where the AGN fraction is high, basically you see an increased fraction of outflows in these galaxies. This instead is coming from Darshan paper for the super survey, showing also the result from the Cache-Z survey with KMOS. And again, at redshift around 2, basically all the objects show very broad lines in the oxygen tree that are sign of the presence of fast outflows driven by the AGNs. So these outflows are not so easy to understand, also because they are a multi-scale and multi-phase phenomenon. So we have outflows around the nucleus of the AGN that we observe through a very highly ionized gas from UV and X-ray lines with velocity close to the speed of light. This is just one example in PDS 456 from Emanuele Nardini some years ago. And then you can go to galactic scale, where you can also explore the molecular and atomic neutral gas. And this is a very famous example from Markarian 231 by Ferruglia and collaborators. Here the velocities are lower, between hundreds and thousands of kilometers per second. And also you can explore the warm ionized gas, especially from the broad wings of optical lines. And again, the velocities are around hundreds and thousands of kilometers per second. There are just few examples of objects where all the phases have been observed. This is an example in the local universe, again, Markarian 231, where you get all the outflows from H1 to COOH, sodium in absorption, and in the X-rays from the nuclear ultrafast outflow. These are just an incomplete list of other examples, but that are still too few to have a complete view of what's happening in this multi-phase phenomenon. This is another example at high redshift. This is my favorite source, XID 2028. This is a quasar redshift 1.6. And again, you have an outflow in oxygen 3 in the warm ionized gas. This is the same thing observed with NIRSPEC, in CO with ALMA, also in the neutral gas in magnesium and so on. And these are other examples of objects with different phases probed at high redshift. With the data we have, we can compute the outflow rates, and this is certainly something interesting to understand how effective are these outflows in removing material from the host galaxy. These are a couple of examples of these attempts from Stefano Carniani 2015 and Fiore 2017. From these plots, you see that that it seems that the molecular outflows are actually dominating the mass budget in the outflow, although maybe at a high AGN volumetric luminosity, the ionized outflows is reaching the molecular ones. However, there are many caveats in this kind of business. Again, few objects in these plots are observed both in the ionized and the molecular phases. So these are different objects that we plot in the different phases. And then there are large uncertainties in the derivation of these numbers. So this is basically, you have to compute the mass of the outflowing gas, and this depends on a lot of things. For in the molecular phase, from the alpha CO, the CO excitation that you assume, and the ionized gas from the density, you have to assume the metallicity and so on. And then you have a geometrical and projection effect to derive both the velocities and the radius. So these are very uncertain business. And this is a compilation for a nice review about the AGN effect on star formation that came out just a few days ago. That is shown using more modern samples of galaxies with molecular gas observations that are not biased towards the very bright CO sources. You start seeing that this line from Fiore 17 might be not a general position of all the galaxies once you add different kind of sources. These are type 2 quasars and ULIRs from these two papers here. So the picture is maybe more complex than we thought just a few years ago. another attempt is try to connect these different scales. So what is happening in the parsec region traced by highly ionized gas and in the X-rays to what is happening on galactic scales, and also to understand how these winds are expanding. If they are dominated by a momentum-conserving wind with low efficiency when the medium can efficiently cool, or it is driven by energy-driven bubbles with much higher efficiency. So this is a business that started with this paper in 2015 by Francesco Tombesi and collaborators that has shown that at least in one case the ultra-fast outflow in the nucleus and the galactic tail winds were sitting were linked together in an energy-conserving frame. However, with more observation, it is again became more complicated. This is a more recent paper by Bischetti in 2019. And again, you see that the points are starting scattering around this plot. And this is another attempt made by our group in Arcetri to use the ionized winds instead of molecular gas. And again, it seems that they are more compatible with momentum-driven winds. This is a compilation of everything we have connecting ultra-fast outflows in the X-rays with galactic tail winds. The line here is the prediction for momentum-driven winds, and the orange point here is the prediction of an energy-conserving scenario. And you see that the points are more or less all of them in between these two predictions. That is already very remarkable to me, also because what is happening now in the nucleus that's a different time scale to what is happening at a larger scale in the galaxy. So it's already remarkable that you have somehow a connection between the two phenomena, but very few targets. So we tried to explore more this kind of acceleration mechanism, making a detailed modeling of the kinematics of gas in nearby AGNs. This is a sample of AGNs observed with MUSE already many years ago. I think the first paper of the series came out in 2015, but the data are so good that we are still working on them. And in Arcetri, we developed this new 3D modeling tool that is called Mocha 3D. Here the idea is that the medium that we want to study is very clumpy and very complex. So the very complicated velocity dispersion map and momentum zero maps may not be due to an intrinsic complexity of the kinematics of the gas, but might be due to the fact that the medium is very clumpy, and so this complicates the interpretation of the kinematics. So what we are doing is assuming a velocity model. For example, in this case, we assume a constant velocity outflow, and we develop a Monte Carlo model in which that is populated with random clouds in this three-dimensional kinematical model. And then what we do is we basically weight each of these random cloud with taking into account the observational effect, so beam smearing and binning, and weight them according to the measured flux in their corresponding spaxel in the observation in space and velocity to reproduce the line profile in that spaxel. In this way, we obtain a tool that is very useful to reconstruct in 3D, assuming just a very simple velocity field. And this is an example. You see, assuming a simple unweighted kinematical model, what you get is that something that resembles very closely the observed velocity and velocity dispersion map, just assuming that the medium in the ISM in the galaxy is not uniformly bright. And this is the application of four of the galaxy of the sample. You see the first row, there is the data, the model in the second row, and this is the residual, all plotted on the same scale. Here we are not only modeling the outflow, but also the galaxy disk. And you see that despite the diversity in the kinematics of this galaxy, the model makes a great job in reproducing the observation. If we plot the velocity of the outflow as a function of the distance in this galaxy, normalizing them for the average velocity in the first kiloparsec, we find that all the galaxies show a similar behavior. So they start with an almost constant velocity, and around 1 kiloparsec, something happens, and the velocity increased by almost an order of magnitude. Remarkably, this happens, the distance is scaled in physical units. So for example, there are some galaxies that are not observed till, in the Muse data that does not cover the part in which the outflow accelerates, and they are consistent with all the others. And this is remarkably consistent with with the expectation of simple models, for example, the famous King model, where you have at the beginning a momentum-driven expansion of the wind, and then when the cooling time is more or less similar to the wind flow time, around 1 kiloparsec, what happens is that it becomes an energy-driven bubble, and it accelerates to a higher velocity. So this would be interesting to test this also on a larger sample, but this is a very interesting result in my opinion. Then in the acceleration of the outflow, there could be also a role of dust. There are evidences that obscure quasar show winds that are faster than normal quasar. This is a plot from a work by Perrotta and collaborators in 2019. These are a sample of blue quasars, and this is a sample of quasar with very high I-WISE color. And you see that the velocity is much higher for a reddening quasar. This is something similar that Giulia Tozzi and Darshan discovered with the super survey. I think Giulia has explained this better later tomorrow, I think, with the flash talk. But again, we find that type 2 AGNs at redshift 2 show faster outflows for given bolometric luminosity of GN than type 1, and this corresponds to type 2 are objects with higher column density also observed in the X-rays. But then, okay, we have fast outflows, but are these outflows fast enough to actually remove the gas from the galaxy? The answer is not easy. To this question is not easy. These are two examples of an attempt to study this. This is a sample of local ULIRGs, and as a function of the luminosity of the AGN, the escape fraction is plotted, and you see that most of the objects have very low escape fraction outside of the galaxy. This is again the same paper by Giulia Tozzi. Is making the same experiment at redshift 2, and you see that the velocities we observe in the winds are borderline to be able to escape to infinity, or at least from the galaxy. So it's still hard to answer this question. There are several other works trying to do this, and the results are mixed. So it's really hard to answer this question. Also, given the uncertainty due to the projection, it's not easy to measure the velocity, because there is also an inclination effect that is hard to disentangle unless you have some kind of very refined 3D models like the ones I showed you before. So the people have tried to check the effects of these outflows on sample of galaxies, for example, confronting the velocity of the outflows with the star formation in the host. These are a couple of examples from low redshift quasars. This is from Wu et al. They compared the specific star formation rate as a function of the dispersion in the oxygen tree for type 1 and type 2 AGN and normal galaxy. And you see that the distribution of the AGNs seems to suggest that actually the specific star formation rate is increasing for faster outflow. outflow instead of decreasing. This is another similar attempt by Balmaverde and collaborators, and again, there is no correlation between the velocity of the outflow and specific star formation rate. This to me is not so surprising, given that the time scale here is completely different. So what people is trying to check is instead there is a direct effect on the gas reservoir that we are observing. This is again XID 2028, where we could measure the molecular gas from ALMA observation. What we found that the gas fraction in this object is very, very low, around 5%, and this despite the fact that it's forming stars at a very high rate. So what you get is that it's around 2 orders of magnitude lower than you would expect from main sequence galaxies at the same redshift and mass range, and the depletion time is very short. So at least in this object suggests that the outflow is actually effective in removing the gas from the host. It's not clear, however, if this is true for the general population. This is, again, an attempt to measure this in quasar below redshift 0.5. And again, type 1 and type 2 quasar doesn't show a clear difference from normal galaxies in the M gas versus M star plane. This is another work instead by Michele Perna. That is measuring LCO against infrared luminosity and the gas fraction as a function of redshift, and comparing a obscured AGN with the main sequence galaxies. And in this case, we find a hint that the quasars show somehow lower gas fraction. Then Elena, in the few talks, will show her work using the combination of the CAS-Z and Super Survey as a redshift 2. That is the largest sample of AGNs with ionized and molecular gas measurements. And she finds that actually the AGNs show a different distribution in gas fraction with respect to the normal star-forming galaxies. So this is, again, something very debated in the literature, but there are some hints that maybe the AGNs are effective in decreasing the gas fraction in the galaxy. Then something even difficult to look for spatial effect, spatial evidence of feedback in the host of the galaxies. There are some attempts to detect narrow H-alpha components due to star formation in quasar, and there are some papers that found an anti-correlation between the position of the outflow. Here is shown, this is a kinematical map showing the position of the outflows in 2 of the quasars by Stefano Carniani, and the position of the star formation shown here in this map. So it seems that the star formation is anti-correlated with the position of the fast outflow. However, this is very uncertain because H-alpha can be prone to extinction effect that are not fully under control. So the idea is, okay, let's search for anti-correlation also from obscure star formation traced by far infrared emission. This is what Isabella Lamperti did a few years ago, again using the redshift 2 quasar from Super. But what we find is that there is no clear trend with the position of fast outflow. This is an example. Basically, this shows in white the far infrared emission, while the black are the contours of the blue wing, the red wing, and the rest frame emission of this quasar. And there is maybe some hint that there is an anti-correlation, but the resolution is not enough to give a definite answer. So another interesting topic is the role of radio jets. So classically, the feedback has been divided in 2 different modes, let's say, an ejective radiative mode driven by this kind of outflow we talked in now, and then a maintenance mode that is dominated by low power, by radio jets that are keeping the gas hot, preventing the inflow of gas on the galaxy. However, there are increasing evidence that there is a connection between outflow and radio jets, and also at low radioluminosity. And this could also have an effect, a direct effect on the ISM of the galaxies. This is some example. This is, again, a work by Giacomo Venturi using MUSE data of the Magnum galaxy. And what he finds is that in this galaxy, for example, 5643, there is a is a low power radio jet in the nucleus that is aligned with the direction of the outflow that is, and the ionization cone that is traced here in green by the emission of the oxygen tree. But what we find is that despite the fact that there is a high velocity gas along the direction of the cone of the AGN, there is broad oxygen tree emission in the direction perpendicular to the radio jet and the position of the outflow. This is not an isolated case. There are several papers in the literature that are reporting something similar. This is another example, again, with the oxygen tree velocity dispersion perpendicular to the direction of the radio jet and of the outflow. And this is a work by a PhD student in Florence that added to the Magnum galaxy also some points at higher jets with higher radio power. And there is a hint of a correlation between the power of the radio jet and the energy injected in the turbulent region characterized by broad oxygen tree lines. So this could be a direct effect of jet-induced turbulence in the disk that is preventing star formation rate. In fact, for example, in this galaxy, all the central part, there is very few star-forming regions, and all the star formation is happening outside the central part of the galaxy. This is another example, instead of high redshift, of interaction between the jet and ISM of the galaxy. This is again XID 2028. This is just a comparison of the quality of the data between the NIRSPEC observation obtained in the early release science program and what we get from the ground with Symphony. You see the incredible amount of details in these channel maps that is possible to get with JWST with what we could get from the ground. And what we found, and there is this very strange shape in the outflow that before was just a very collimated and nice oxygen tree wing. With NIRSPEC, you start to see that the outflow is detached from the position of the AGN marked with the cross, and there are kind of filaments that are connecting this outflow with the position of the nucleus. This is the picture shown before. The oxygen tree outflow is actually aligned with the position of the molecular outflow. And what we discovered is there are some VLA observations that are showing two lobes at the position of the outflow. So our interpretation of this is that what we are seeing is that there is a radio jet that is inflating a bubble in the ISM of the galaxy, creating these filaments, and at a certain point the jet is able to escape from the bubble and is producing the very fast outflow that is extending at large distance from the galaxy. This is a 3D representation of the Mocha 3D model of the oxygen tree emission within this galaxy that confirms that this kind of modeling with a bubble plus an outflow is able to reproduce the data. So I just have a few minutes left. Another interesting finding of JWST is that we are discovering a very large population of faint AGN at high redshift, mostly from the presence of broad lines in the Balmer emission that are not present in the other forbidden emission lines. So these are all interpreted as broad line region that, from low mass and faint AGNs. This probably has an implication from the feedback at high redshift, given that the AGNs are possibly much more than we were thinking. The problem is that these kind of AGNs are only detected by the broad lines. So we are probably missing a full population of AGNs that are not showing broad line, but we are not able to detect. This is also because the normal approach we are using to discriminate between AGN and star-forming galaxies are not working anymore at the low metallicities that we find at high redshift. This is again an example. These big stars here are one of these hidden broadline AGN in a redshift 5.5 galaxy, and you see that in the BPT, this galaxy sits at the edge between the star forming and the AGN galaxy on the BPT, and actually the outflow that is driven by the AGN is just sitting in the star forming galaxy part. It's exactly where all the normal star forming galaxies at the redshift are sitting in the diagram. These are model grids by Nakajima and Maiolino, and showing that everything AGNs and star-forming galaxies are all sitting there. This is another example from more broadline AGNs, redshift 4 to 7 by Arikane 2023. Again, both galaxies and AGNs are sitting there. So the idea is that you need some other probes of the presence of AGN. One possibility is to use helium-2 emission. This is the diagnostic diagram built using Manga Galaxy by Giulia Tozzi last year. And this is in principle possible to apply it at high redshift, where the AGNs and the galaxy are well separated in this kind of diagram. And the same target I showed you before by Hubler is clearly in the AGN part of the diagram using this kind of diagnostic. And I think my time is finished, so I'll skip the future and I'll leave you the conclusion. Sorry.
Yeah, question back there.
Hey, Giovanni, thank you very much for a great overview talk. So can you talk a little bit more about the relationship of that feedback with the radio structures that you're seeing? Can you confirm that all of the radio structures are confirmed jets? Because when you were talking about, you mentioned the Harrison and Ramos Almeida paper that just came out a couple days ago, and they're talking about like the radio could also be due to shocks in the ISM, and so and they say it's observationally challenging to disentangle between jets and outflow-induced shocks. So
yes.
Are those confirmed jets, or do you have as a potentially due to shocks?
Some of them are for sure jets. I mean, they are extended, and their morphology is not exactly following the shape of the ionized gas outflow. In some cases, there is this possibility that actually they are not jets, but as you said, could be due to shock in the ISM due to the outflow. So it's not fully clear. In any case, it's not fully clear why the jets are creating this strange structure in the ISM. So I agree that in some cases, it's not clear-cut if they are really low-power radio jets or not.
Is the molecular gas in the molecular outflows produced in the outflows themselves, or is it coming from the galaxy? This is the first question, and the second, could you explain better the acceleration of the outflows further out in the jets when they are already going out? You talk about dust, pressure by the dust. Could you explain? Well, two questions.
Okay, so sorry,
first
I forget.
Was if the molecular gas.
Okay, yes. This is a very hard question. It's probably for the theoretician in the following session. I mean, there is just at least one example where it looks like that the molecular gas in the outflow retained the circular velocity that it had in the disk. So like the wind from the AGN is bringing the gas outside the disk, but it retains some of the rotational velocity of the disk. So in this case, it looks like that at least part of this gas is not produced in the outflow, but it's removed from the disk. But then how it survives, and this is, I don't know. I don't know how to answer. And also the other question, I'm not sure I can tell you more than what I said. I mean, there is some indication that the dusty galaxies with a lot of dust show faster winds. So it could be that the coupling between the wind itself and the ISM in the galaxy is higher because the radiation pressure is more effective on dust, and this helps in accelerating these winds. But I think this is, again, not well established. There are some examples, but there are other papers that compare dusty objects with non-dusty objects, and they found similar velocities. So again, everything is very uncertain, mostly because to measure velocities, even more mass outflow rates, is a very detailed modeling of the three-dimensional geometry, and this, especially at high redshift, is very, very difficult. Okay. So I think where we can really improve to understand what's going on is to get this kind of three-dimensional understanding of what's going on.
Okay, thank you.
Okay. Unfortunately, I think we're going to have to move on to the next speaker, so questions will have to be done offline.
Thanks.
Where's the mic? Giovanni,
Ah, sorry, yes. It was a very nice microphone. But
you have the best audience questions.
sorry. But at least I left the pointer somewhere.
All right.
Okay, while we're getting set up, I'll introduce the next speaker. Jason Young is going to be talking about Halfway to the Peak, a bridge program to map coeval star formation and supermassive black hole growth.
Try speaking on that.
Check, check. All right. Well, thanks to the organizers for bringing us all together, and a special thanks to my fantastic collaborators without whom this paper and this project would not be possible. My name is Jason, and we'll be going not back to cosmic noon, but halfway back to cosmic noon. So our program is called Halfway to the Peak. We're looking at galaxies at z of 0.5, which is chronologically halfway back to cosmic noon. And if you're wondering why this era is interesting, there's a lot of reasons. So we're looking at a transformative era where cosmic star formation rates are declining from cosmic noon, but still 3 times higher than they are today. This is also, incidentally, the era when the Milky Way formed most of its stars. So if you're interested in the Milky Way, then z of 0.5 is actually kind of an interesting time period. We've been seeing a lot of research about how James Webb has unveiled dusty ISM conditions in low redshift galaxies. For example, this beautiful plot from Lai et al. 2022, where we're using these mid-infrared diagnostics with spatial resolution to really pick apart the details of how AGN and star formation can influence their host galaxies and how they feed back to each other. Our project tries to do something similar, but with much more distant galaxies. To do this, we need the reddest instrument on JWST, MIRI-MRS. So MIRI-MRS has 4 channels, each with 3 grading settings. And to get full wavelength coverage from 5 to 28 microns, we're going to use all of them. So that makes this a somewhat expensive program, 2,000 seconds roughly per grading setting per object. We have 7 objects. These are all luminous infrared galaxies. So because most star formation at this time was in dusty galaxies, these are a good sample of what was going on at z of 0.5. But they're chosen to span a range of AGN fractions from star formation dominated at the bottom to AGN dominated at the top based on these Spitzer IRS spectra. There we go. Okay, to get us there, we need to push MRS to its limits. Because we're at z of 0.5, we're not doing local galaxies. These are going to be fainter objects, even though they're very luminous. And so the basic pipeline, which does a pretty good job, is not going to be quite enough to get us there. We needed to go through a bunch of several iterations of tweaking the pipeline, doing some custom sky subtraction, custom background subtraction techniques, And you can see this montage over the course of about 6 months, us getting closer and closer to the polished data cubes, which reveal the spatially extended objects. So we can do spatially extended, spatially resolved spectroscopy at Z of 0.5. Okay, to see how far we've come, I've got the Spitzer IRS spectra. Now with R of 100, we can pick out the overall shape of the continuum. We can see some of the broader pH bands, a few atomic lines, but we are fairly limited. With JWST, we can pick out a lot of atomic lines with crisp resolution. The pH line bands are now deblended from other elements in the continuum. We unlock this ensemble of ISM diagnostics, so we can really get at a holistic view of what was going on in these galaxies. Just to highlight a few things that we are seeing in our data, we have a number of atomic lines, some recombination lines, which are direct star formation rate indicators. We have, as I mentioned, several pH bands, 3.3, 6.2, 7.7, 11.3, each of which are probing different sizes and ionization states of the pHs. So we have multiple diagnostics of current and recent star formation. We'll circle back to that later. The hidden neon 6 line that sits right on top of the pH 7.7 micron feature. This is a direct diagnostic of black hole accretion rates and potentially black hole accretion disk kinematics. Not possible to see in the earlier spectra because it's totally blended with this bright pH band. There are a suite of H2 rotational lines, which are diagnostics of warm molecular gas. One of our team members is working on an H2 sled to see what the warm molecular gas is doing in these galaxies. So with full wavelength coverage in this range, we actually can do a lot. This is the first paper we put out on our first, most morphologically interesting object. We're taking advantage of the fact that we have spatially resolved spectra to look at different regions within the galaxy. We see different ISM conditions across the galaxy. I've got a montage of the spectra here. I'm just going to highlight a few of the science takeaways that we found for this object. There we go. All right. So with the atomic lines, we can do kinematics. And if you're interested in this, we have another fantastic talk coming up by one of our team members, Miriam Eliezer, who will look at kinematics across the entire sample. This is just a highlight from FLS1, where this luminous infrared galaxy, halfway back to cosmic noon, has a stable rotating disk. Looking at the spatial extent of the features, we see that, as I mentioned before, we are getting spatially resolved spectra. So on the graph on the left, we've taken a cube that's been blurred to a common beam, so we've removed all wavelength effects, and we're comparing several star formation and warm molecular gas diagnostics, and they're all more extended than the full-width max. But we can also see that they're very compact. The core is actually contributing a lot. So to get at the spatially extended wings of the object, we're going to switch over here to some contours placed at 50, 25, 10, and 5% of the peak value. And one of the things we found in this object was that the pHs are more extended than the atomic tracers of star formation. Now, as I mentioned before, they're tracing star formation in different time scales. So the pHs are roughly tracing star formation on 100 million year time scales, whereas the atomic tracers are more like 10 million year time scales. So the simplest interpretation is that in the past 100 million years, star formation in this particular object has become more compact. That's probably right, although, of course, as we all know, the ISM and the pHs are complicated, and so we're exploring other interpretations. So put a pin in that one, but this seems to be the most likely explanation. So one question we could ask is, does this hold true across the entire sample? Are we catching objects at a time period when their star formation is becoming more compact? The short answer is no. The sample spans a range. So here's a preliminary plot from a paper that we're still working on, where we see the same contours with the same meaning only this time we see that they really, really do span a wide range of spatial extents. So we're seeing a heterogeneous sample, most likely heterogeneous in star formation history, at least recent star formation history, but potentially heterogeneous in other ways that are influencing these diagnostics. But to really get at a quantitative analysis of the PAH diagnostics, we need to look at flux ratios, which means we need to do a full SAD decomposition. So this is possible with these spectra because the high resolution allows us to deblind different features. So we're using a software called CAFE, which lets us do mid-infrared SAD fitting and decouple a lot of the features which are either blended or very close to blended. For example, the 11.3 micron feature sits right next to the 9.7 micron absorption trough. And so we actually do need to do this decoupling to get at all these features. And these pH bands, like I said, trace different ionization states, different grain sizes. So we're really going to learn a lot about the ISM in sort of a holistic way. Now, if you apply for MIRI MRS time, one thing to bear in mind is that in addition to using the MRS IFU, you can simultaneously use the MIRI imager. So we did that with our program and collected some deep MIRI imaging data of basically random fields next to our targets. And with that, one of our team members, Leo Sechkov, is working on the number counts analysis in these deep mid-infrared images, which roughly correspond to IRAC-3 from the Spitzer era. And what he's finding is that the number counts are roughly consistent with what the Sears team found given expected field-to-field variations, and slightly higher than the model expectations. So stay tuned for the paper that's impressed in this one. Okay, so to sum up, MIRI MRS is a fantastic instrument to see the dust-obscured conditions in star-forming galaxies. It is, in my opinion, one of the more complicated instruments to use, but well worth it, especially if you're willing to go the extra distance to push it to its limits. With this, we've been able to unlock star formation rate indicators across different timescales, ISM conditions, black hole accretion rates, and kinematics. The star formation rate tracers show different spatial extents, and so we're hoping to learn more about the recent star formation histories of these objects and put them in the context of galaxy evolution. To do that, we'll need a full spectral decomposition across the spectral range. With that, I'll open the floor for any questions.
Thanks. Yes, Emerald.
Hi, really nice talk. So I was wondering, since you were showing like the different spatial extent of the different star formation rate tracers, so I was wondering if you have like ALMA data and like have you looked at like the extent of molecular gas and how that correlate with like the pH extent?
Yeah, we haven't really looked at the spatial extent in ALMA data. We're trying to, we do have the Spitzer IRS spectra, but that of course doesn't give you a whole lot of spatial data. So right now, what we're working with is sort of the best we have. And so we're learning what we can from this. But that's a good idea to try to look at what ALMA data might say.
Yeah, Janice.
So on the blue side, your spectra cover the 3.3 micron feature, but it's not there. Is that a effect just because it's at the edge of what you're covering, or is that real? That's not detected?
Okay. So I am glad you asked. Because the interest in the PAH 3.3 micron feature is obviously rising. It's the bluest PAH feature. So as we go to higher and higher redshift, it's the last one that will be lost off the red end of any instrument you care about. And we were hoping we could say something really cool about it in our data. And this is where it would be. But I have to admit, we don't really detect it. And
is that non-detection robust or not?
TBD.
Okay,
so
thank you.
We are seeing structure in that part of the spectrum, and we're trying to figure out if it's some issue with noise because it is on the blue end. The blue end is supposed to be better behaved, though. There's the 3.3 aliphatic feature, which we think we're seeing, TBD. But I will say, if it's there, it's not super bright.
Okay, we have time for one more question. Darshan?
Thanks, very nice talk. I was wondering, like, so you see extended pH emission, right? So have you checked or have you made a map of the pH ratios as a function of, say, the center? Like if the AGN is doing something to the pH ratios or not?
We have, and we do find, so I'll say preliminary evidence of enhanced pH ionization near the centers of the objects. That'll be in the paper that will come out in the next month or two.
All right, great. Let's thank the speaker again.
I think you've got a low battery. 1 bar. Just stay near the podium.
Hello? Yeah.
All right, great. So this is the last talk before coffee. Tameya Nanayakara is going to be telling us about insights into early star formation histories from Z greater than 3 massive and quiescent galaxies.
Yeah, so it's not a little bit about AGN, but I will try to mention the word towards the end, so still goes well. So just want to give a quick overview of where we are in terms of finding these quiescent galaxies at a little bit of redshift 3 to 4 era, and then try to bring out the big picture of how these galaxies quench and then how they probably formed at early times. So there has been a lot of work done even before JWST came online, because we had this suite of nice ground-based and space observations. So we could do make some observations based on the Balmer break from photometry, then use this UVJ color diagram, which kind of really helps to find the quiescent galaxies and distinguish them from star-forming and dusty galaxies. And observations did show that these the ones that we choose do actually have very low star formation rates. So ground-based spectroscopy was really good in finding and confirming these sources. As you can see, this is either MOSFIRE or X-shooter spectroscopy from some of the work people have done, and you can see they are kind of expected to be quiescent because you do see some of the hydrogen absorption lines. So I just want to take a step back and then look at one of the deeper data we had. This is like a redshift 3.7 galaxy that we had from MOSFIRE, one of the first galaxies to be confirmed to be quiescent at redshift 3. You can see nice hydrogen absorption lines. And of course, with JWST, we get now the full spectrum of these things. And you can imagine the equivalent width of these sources, because like you can even see in the PRISM low resolution data how strong the absorption features are. And not only that, you do see very strong sodium and magnesium absorption. And the resolution is about 200 to 300, so it has to be extremely strong. So it brings up new nice pathways. But one thing that became clear is that NIRSpec PRISM is a really good way of finding these quiescent galaxies, because we can observe a ton of them together. And then because of this break that happens around 2 to 3 microns based on the redshift, you can get D4000 or Balmer breaks that kind of gets us to distinguish between different degenerate scenarios, which sometimes plagues photometric selection techniques. So yeah, that's how DALI thinks JWST looks like. But we do have a lot of spectra from JWST now, and as you can see, these were sources that we could not confirm from the ground for most of them. And clearly, most of these galaxies are quiescent in terms of having a strong Balmer break. And there are some emission lines in them. I will come back to them in a bit later on. And our sample, which was selected from CForge and 3D HST surveys, goes from our redshift 3 to about 4.5 or so. So some of the galaxies, it was possible to observe from the ground because they had these strong emission lines. So you can get it from MOSFIRE from the ground, but not all spectra was possible, because if it was kind of a scenario of some sort of a luck, because if you have a galaxy like this one where I had the emission line just towards the end of the part of the K-band atmospheric window, you could not confirm these galaxies. So there were some nice, interesting galaxies. I will highlight a couple. This is a redshift 4.3 source. This is the SCD we had. And if you look at this, you probably won't believe it. But because the K-band was quite deep from ZForge, there was kind of tentative evidence that it must be correct, but the redshift was way off, like 3.3. But with NURSPEC, we can confirm it to be around redshift 4.3, and with primer data, we get a nice SED confirming its quiescence. So one of the most important things is not just finding them, but try to understand how they form and evolve, right? So for that, we had to do like SED fitting, and there's a lot of degeneracies that come into play. But because we have a large wavelength window with spectral, like covering from 1 to 5 microns, which gives the full optical part of the spectrum and a little bit of the near infrared as well, we can use different stellar population models and see what comes out. So on average, we find that regardless of the stellar libraries or stellar population models we use, we do get a similar distribution where most of the galaxies slowly evolve, and then around like about 1.5 billion years after the Big Bang, they kind of form rapidly to form most of the stellar mass. Am I going the back side? Yeah, I'm going the other way, I guess. Oops. Yeah, so one problem is, of course, we don't know whether that is a ground truth or not. So what we can do is we can take simulated data. This is from the illustrious TNG simulation. We took around 280 or so quiescent galaxies at redshift 3, looked at their star formation history. So this is the median star formation history you get, and then you kind of use all the 200 galaxies, make 200 spectra for redshift 3, and then refit them with the same method you use. And you can see in blue the reconstructed star formation history. It agrees very well with the dark brown line, which is kind of the input parameter. So kind of gives an idea that SED feeding codes are kind of doing a good job in finding them. So we can now compare with what Illustrious finds with what observations find, and you can see the overall shape of the observed data, which is shown in green, is kind of follows very well with what is shown with the simulation. So it's kind of accurate to say for the overall average population of galaxies, which are quiescent around redshift 3 to 4.5, simulations are doing a good job in getting this average, like kind of the buildup of mass for these early galaxies. But there are, of course, always outliers when you do observations, and Z47329 in one of these outlier galaxies. So in blue, I show the T50 when the galaxy formed around 50% of its stellar mass. It's about 10 to the 11 solar masses. And then this is the time when we consider the galaxy to be quenched. So with ground-based imaging, we had like some constraints, but JWST, as you can see, we get the tighter constraints to the formation timescales, and you can clearly see this galaxy kind of expected to form around redshift 10 and then to be quenched for more than 1 billion years by redshift 3. So it's kind of a very like early source to have quenched. So, but what we can also do is then do a comparative study with the simulations again and see where things lie. And this is clearly an outlier at the current time, because if you take the Eagle or Flamingo simulations, you can see these two lines for different baryonic conversion factors. It's still not there yet in reproducing the star formation history of this galaxy, which is shown in green and red for different SED feeding codes. And you can clearly see this galaxy preferred to have formed most of its mass before redshift 10. So it's about like 10 to the 11 solar masses in the first few 100 million years of the universe. So it's kind of like a very early starter, but of course, you don't expect outliers to be produced in a simulation, because the whole idea is to get the general population. But nevertheless, it's important to see if there are more of these sources that we find, which can then kind of try to challenge some of our observations. This galaxy also has some of these nice AGB kind of features that you see in the local NGC galaxies, which kind of gives another independent confirmation that there is some very old stellar population hiding inside this source. And recently, there was another redshift 4.9 galaxy found by Anna de Graaf at redshift 4.9. And you can see this galaxy is also expected to be quiescent. And when you reconstruct the star formation history, you find exactly the same thing, where most of its stellar mass was formed around redshift 10. So it's kind of a similar stellar mass story, like a very old system. But there is a degeneracy with metallicity, as you see. But things seem to be worked out. But kind of it is pointing towards the fact that there are more of these very old galaxies. So we can now put it into context. Is Ryan in the room? No. Okay. So like we had a long discussion about this figure from which came out soon after JWST data. So some of these points have since moved. At least 2 galaxies have to be confirmed at lower redshift. But it did show that there might be a population of very massive galaxies in the early universe. So we can now try to see where our kind of these massive quiescent galaxies between redshift 3 to 4.5 fall in this scenario, because you can reconstruct the star formation histories. And you can clearly see at around redshift 8 to 10, they should fall around the same region where this initial data has come to be finding these massive systems, but more work is to be needed. These galaxies are quite different from the other population of these smaller post-starburst-like sources that we find at redshift 7 or so, because these are much smaller mass systems. So I think there are 2 different things going on in the early universe, where there's a population of sources which formed very early, very fast, and then suddenly quenched because of the passive evolution and finding this like the 4000 features in these galaxies. And then you have these starburst-like galaxies which keep on slowly building mass with time. So in the last few minutes, I'll talk about the AGN, because as you might have seen, some of these galaxies do have strong emission lines in them, which kind of points towards the fact that they might have some sort of AGN activity going on. So if you zoom into the O3 and H alpha emission line of these galaxies, you can see the broadening is very high, about 10,000 kilometers per second or so. So it kind of gives an idea that there's definitely some AGN activity going on. So the question becomes, is the AGN activity driving the quiescence of these systems, which kind of could explain how they quench so fast. But coming back to the whole thing of finding these galaxies, the AGN does not seem to have a strong effect when you put like AGN effects into SED modeling. This rest frame UVJ colors still seems to indicate that we can find these galaxies in high efficiency. So while the quiescence might be happening, it's still a good way to still use this new JWST data to find more of these high redshift sources to explain them. And at least in the HST selected samples, except for 2 galaxies, I think, in our sample, all the other 18 galaxies in total is expected to be quiescent at these redshifts. So it kind of, we are now increasing the number density of these sources. Proper work needs to be done on the overall distribution, but also the fun thing is about understanding these outliers in the universe as well. So I think I'll end up there just saying that our selection techniques are still working. We are finding good things. Simulations are doing most of the job very well, but there might be some outlier sources, and it only will become a problem if we find more of these sources. Before I end, I'll give a small plug into the IAU meeting. We and Katie and some other people organizing for JWST stuff in Cape Town. So if you're going around, please do come and say hi at that time. Thank you.
Okay, questions? Yeah.
Hi, really nice talk. So I am intrigued by like your last slide about like the AGNs. So have you looked at the line ratios and see where they lie?
Yeah, so they kind of lie. So because the problem with the PRISM data is you cannot really resolve the full BPT, but you can do the mass excitation diagram, and almost all of them suggest that they are highly ionized, pointing towards AGN. So, in that figure that Steph. So if I remember Stephanie's plot, it had this kind of 2 regions. So most of them fall in the pure AGN region, and there's a mixing region. Some of them fall. So yeah, so but it depends on how much you trust, because there's a lot of other ionization that can affect the same line diagnostics, but it is pointing towards that. Yeah.
Yeah, one more question, then we'll go to coffee.
So in terms of the assumptions going into the SED modeling, is this all pointing to the fact that it's probably best to use some kind of birthday / non-parametric star formation history model to reproduce what you're seeing in the observations?
There's not a very big difference. So I didn't really, there were 2 different codes I used, Prospector for the bin of non-parametric star formation histories, and then for, and the other one was, of course, was fast plus plus. I don't know, but if you look at the distributions between, oh, come on, they used the wrong slide. because they don't show you the thing. Anyway, but blue is prospector, red is fast plus plus parametric, and both of them do produce the same, overall same star formation history. So as long as there's enough flexibility in your parametric model, you can recover it, I think, but of course it's better to use a binned star formation history to be 100 more accurate. Yeah.
Thank you.
Okay.
All right, let's thank the speaker. And maybe an encore thanks to all the speakers in the session. Okay, so we're going to coffee and we'll reconvene at 3:30.